Okay, this is going to be 5.2. All right, so starting at question 2, you have an initial investment of 75,000 increases, so that's growth. So your function is going to be A equals P 1 plus R to the T power. So our initial investment is 75,000. Your growth is 12.5%. So that's going to be 0.125. So 1 plus 0.125. So we're going to add that to 1. That's going to be 1.125. So we have 75,000, 1.125 raised to the T power. So that is your function. So it'll be this one, 1.125. So this problem wants you to calculate it. So this is number 2. So we're actually using the same function here, 75,000, 1.125 to the T power. We want to know what's it going to be like after 30 years. So let's plug in 30. 30 is going to be your T. So we're going to plug in 30 up there. And let's do 75,000, 1.125 to the 30th power. And 2568247. 0.87. I like to do dollars and cents, so I'll do 2 decimal places. That's number 3. Okay, question 4. 4 and 5 are going to be similar like 2 and 3 were. So you have your starting amount. It decreases at a rate of 1.4%. That's 0.014. And it's decreasing, so it's going to be decay, which means A equals P 1 minus R to the T power. So 752,000, parentheses 1 minus 0.014 to the T. So 1 minus 0.014 is 0.986. 752,000, 0.986 to the T power. So it's going to be that one. Now let's answer question 5. What's it going to be after 18 years? So now we want to know by plugging in 18, what you're going to get. And 18 is going to be your T, so we're going to plug in 18 up there. 752,000, 0.986 to the 18. And that's going to be 583,448. It says round to the nearest whole number because it's people. So 583,448 is good enough. And question 6, one more like this. House has been losing 2% of its value over the past several years. The house was originally purchased for $250,000. Let T represent the number of years and A of T represent the amount of T years. So it's been losing, so it's again going to be decay. So your rate is 2%, that's 0.02. So decay is going to be 1 minus the rate. So 250,000, parentheses 1 minus 0.02, 100% minus 2%, which is 98%. You can check that in the calculator. 250,000, 0.98 to the T power. So that's going to be that one there. And so now let's plug in whatever number we want to know. So it looks like it's 20. So now we have our function. We're going to plug in 20. Since it's 20 years, so we're going to say 50, oops, I erased the 2, 250,000, parentheses 0.98, raised to the 20th power. Let's see what we get. And it looks like 166,901 and 99 cents. So we're going to say 166,902. Yikes. 166,902. It's smaller because it's been losing money. So there you go. Number 8. A town had an initial population of 18,000 people. It grew exponentially at a rate of 3.7% each year. To the nearest tenth of a year, how long did it take for the town to reach 50,000 people? So your initial amount, P, final amount, A, grew 1 plus R. R is 0.037. So we got everything to plug in, except we want to know to the nearest tenth of a year. How long? We don't know the T. So let's think about what we're plugging in. 18, our initial amount, 1 plus R to the T power. So our initial amount is 18,000. It's going to go there. 1 plus R would be 1.037. And then we don't know, well, we know our final amount is 50,000 people. Now, if you're watching this video, you likely have learned how to do this using logarithms, but we can still use a intersection of a graph for this if you'd like. So the way to set that up would be to do 18,000 parentheses 1.037 raised to the x power. But then you would do y equals 50,000. And you'd need to zoom out to be able to see. I think I put 500,000. That's a little bit better. You need to zoom out to be able to see where it's going to hit 50,000. It's going to be way up there. And there's your flat line at 50,000. So now we got to go back in. Drag it, zoom in, drag it, zoom in. And you're looking for those two graphs to meet each other. And so that's about 28.12. So T is approximately 28.12 years. It says to the nearest tenth of a year, so you could say about 28.1 years. But 28.1 or 0.12 if you want to go a little bit more out is question 8. Question 9. A population of bacteria cells grows according to the function P of T equals PO parentheses 1.35 to the T power. T is measured in hours. If the initial PO population size was 500 cells, approximately how long will it take the population to exceed 8,000 bacteria cells? So the initial is this number here, which is given to you as 500. This is going to be your PT. That's your final amount. So it's going to be similar to the last problem. We have 8,000 equals 500, 1.35 to the T power. So we'll use a graph again. Again, these can be solved using logarithms, but this lesson actually comes before the logarithm lesson. So I'm using a graphing approach. So you y equals the number side and put the other function in using x. Let me press home and zoom out. And we're looking for 8,000. And I'm seeing about 9.239. So it says nearest tenth of an hour, 9.239. 9.2 is fine. You can go out 9.24, 9.239. As long as you're close, you're good. Okay, question 10. Charlotte's population, current population is estimated to be 912,096 people. The population has been growing annually at a rate of 1.47%. That's 0.0147. According to these numbers and not Google, what was Charlotte's population 10 years ago? And just for your reference, this is what it actually was in 2010. Let's see how close we are to the numbers. So what was Charlotte's population 10 years ago? That was the principal amount. This is your final amount. And we want to know how long. Well, actually, we know how long. It says 10 years ago. So we don't know P. A is 912,096. We got our rate. And it says 10 years ago. So T is going to be 10. So let's set up the problem. It's a growth problem. Where we have our final amount, or close to it. We don't know P, but we know that it's 1. I'm going to go ahead and add the 0.0147, so 1.0147 to the 10th power. This is a problem where I'd use division. So I will take that 1.0147, raise it to the 10th power, and then I will divide it out of the 9121096. Those will cancel out. So you can type it into Desmos all at once, which is what I would recommend you do. It's only going to raise that bottom number to the 10th power. So you'll see your initial amount, which was 788,249.9. So I'm going to round that to approximately 788,250. Now it's a little bit higher than what the actual number was, but it's not too far off. We can double check that. If you do 788,250, in parentheses, you do the 1.0147 and raise it to the 10th power, you get about 912,096. So it gets you back to where it should be. So the division worked. And our last question, number 11. Okay, you have an investment account now worth $25,000. You have been averaging interest at a rate of 4.5% for the past 20 years. This is just like the last problem. We want to know how much did you initially invest? What was the P? This is your A. Rate is 0.045. Time is 20. So let's throw it all in there. Our final amount is 25,000. We don't know our starting amount, but we know that it's a growth problem. So these are all growth, 1.045 to the 20th power. Divide that out. Put that in your calculator, see what you get. Looks like we start about 10,366. Says to the nearest dollar, so we don't have to go out decimal places. It's going to be about $10,000, $10,366 was your starting value. And that concludes 5.2.